Hello and welcome back. In this video we're going to look at calculations involving equilibrium and also approximations that will help make our life a little bit easier. Let's refresh on the process of working problems related to equilibrium situations. Remember that you have two things that you must do right off, and that is set up a rice table from the information in the problem, write your equilibrium constant expression, and then plug into that expression from the rice table and determine what it is that you're asked to calculate. So plug in and crank out. Okay, so here's our problem. It says, if a mixture of 0.78 atmospheres of nitrogen and 0.21 atmospheres of oxygen are allowed to reach equilibrium at 25 degrees Celsius, calculate the equilibrium concentration of each of the substances in the mixture. And here is the reaction that's given. So let's go ahead and set up our rice table from the information in the problem. We are told that we are starting with 0.78 atmospheres. Now we're working with Kp. By the way, the Kp value has to be given. I'm sorry, I didn't write that yet. So our Kp value for this problem is 2.0 times 10 to the negative 31. Now, some of you may remember from the past video that we had the same equilibrium, and the equilibrium constant value was only 0.027. Keep in mind that the equilibrium constant value is temperature dependent. This is a different temperature that we are looking at the reaction. All right, so we have 0.78 atmospheres for nitrogen, 0.21 atmospheres for oxygen. We are not given any nitrogen monoxide initially. That means there was none to begin with. And because we are missing a product, then the forward reaction is going to kick in. So we're going to have minus x. Here we're going to have minus x. Here we're going to have plus x. Plus 2x. At equilibrium then, our equilibrium values would be 0.78 minus x for nitrogen, 0.21 minus x for oxygen, and 2x for nitrogen monoxide. Okay, so that's our rice table. Let's set up our equilibrium constant expression, and I'll just write the value, 2.0 times 10 to the negative 31 is equal to concentration of products, which is nitrogen monoxide squared, divided by reactants, nitrogen and oxygen. Now that we have the expression, we will plug in our equilibrium concentrations into the expression and determine our unknown, which is x. So our concentration of NO is 2x, and that is squared. Keep in mind it's all of it squared. Don't just square the x. Be careful with that. Then we have 0.78 minus x and 0.21 minus x for nitrogen and oxygen respectively. And all of this is equal to 2.0 times 10 to the negative 31. Well, since our initial amounts or partial pressures of nitrogen and oxygen are not equal, this is not a squared term that we could just take the square root of both sides and solve like we saw in the previous video. We're going to actually have to go through the math. So you would go through and use the quadratic equation in this particular situation and then determine x. Or you could use your knowledge of chemistry, what you've gained so far, to see if we can simplify the math. In other words, let's see if we can approximate. So what exactly is the way to approximate, or where do we approximate? If we didn't have these minus x's, these binomials, the math would be much more simpler, right? Well, how can we get rid of these x's? what we need to do is for each binomial, this is a negative, for each binomial we need to see there are two criteria that we have to meet in order to approximate and say that x is negligible. First, we have to have the change in the non-favored direction. And the second criterion is that the value of k compared to the initial concentration of the species in the binomial has to be at least 3 orders of magnitude or higher. The separation of these values has to be at least 3 orders of magnitude. And the greater the difference in orders of magnitude, the more sound the approximation. What do I mean by that? Okay, let's take a look at the value of k. And our value of k is 10 to the negative 31. That is ridiculously small. That is telling us that this reaction, when just a little bit of products are formed, then equilibrium is established. We're going to have very little product relative to the reactant. The forward direction is not favored. And the change line is saying that we have to go in the forward direction. So, our first criterion, we are going in the non-favored direction. That's the forward direction based on the value of k. Now, let's look at the individual binomials and see, can we approximate? Does this mean the fact that the forward reaction is not very favored? Does this mean that x, the little bit of nitrogen that's going to react, is that going to impact, make a dent in the initial concentration, or is it going to be so small that it is not a significant value, it's negligible? Well, our concentration is 0.78, or partial pressure, initial amount of species here. And our value of k is on the order of 10 to the negative 31. Wow, that is 30 orders of magnitude, not even just 3, it's 30 orders of magnitude. That means x is so slight, it is negligible. It is insignificant and will not make a dent in how much we started with. Some of it will react, however, in order to produce some product, but it's going to be extremely small. So now we approximate and say that 0.78 is approximately, minus x is approximately 0.78. We'll do the same thing to the other binomial, 0.21 minus x. Again, the orders of magnitude are going to be very large between this value and the value of k that we're given, so we will approximate here as well. Actually, I shouldn't have marked that out. Just down here, that this is negligible, and at equilibrium we're effectively going to have 0.21 atmospheres of oxygen and 0.78 atmospheres of nitrogen. Now, we come back to our equilibrium constant expression. We have approximated, so now this goes away, and this goes away, and it becomes a much simpler problem to solve. So if you would pause the video and go ahead and do the calculation and determine what the value of x is, and then join me. All right, so you should have gotten x when you solve it and you take the solve for x in the square root. You would have gotten either plus or minus 8.19 times 10 to the, sorry about that, hold on a minute, 8.8 times 10 to the negative 17. You have to, since it's a square root, then the root of that would have either the positive or the negative values. A word about the different solutions that come out when you have the math coming out here. There's only one solution that's practical chemically. And that is, if you think about what X is telling us, this is concentration of something at equilibrium. You cannot have a negative concentration. And so this root is not a possible answer. So we ignore it and we use the other value. Okay, so now that we have this X figured out, what we have to do is come back and plug into the equilibrium concentrations that we had written in our Rice table. Remember that we approximated the partial pressure of nitrogen as 0.78 atmospheres. And if we subtract from 0.78, 10 to the negative 16th, you see how insignificant it is. It's nothing, right? And the partial pressure of oxygen is 0.21 atmospheres. Again, our approximation is very sound here because it's a huge difference. The separation between the initial concentration and the value of K was huge. Okay, and lastly, the partial pressure of nitrogen monoxide at equilibrium is going to be 1.8 times 10 to the negative 16th atmospheres. And that, my dear students, is how you would calculate the concentrations at equilibrium and use chemistry to simplify the math. The two criteria in order to approximate, again, you have to be in the change line. The direction of the change has to be in the non-favored direction according to the value of K. And for the binomials that you're trying to simplify or approximate, the concentration in that binomial, the value of that concentration, and the value of K have to be at least 3 orders of magnitude or larger. The larger the difference between those two numbers, the more sound your approximation. By the way, after you finish, you might want, this problem was pretty clear. However, when you do approximate, what you really need to figure out is to check your work and see, figure out if it's X where you approximated has to be less than 5% of your reaction. So if you calculate, here we calculated X as 1.8 times 10 to the negative 16th versus 0.78 times 100, and this tells us the percentage of reaction that happens. If this is within 5% or less than 5%, your approximation is good. All right, and that's how you would check to make sure your approximation is good. And that wraps up our video.